I'd like to give the floor to Toby Menzies from Core Power, who are in London, which is another maritime application, but a rather different application for molten salt reactors on ships. So, Toby, thank you. We can see your screen. Go ahead.
That's great. Thank you very much, John. And I'd just like to say thank you generally to Progrès Nucléaire for the chance to present this afternoon. In general terms, it's great that advanced nuclear is sort of stepping out from the wings and steadily sort of moving into center stage. And it's a really good lineup that you've assembled today. We're delighted to be a part of it. So thanks for the opportunity. So my name is Toby Menzies. I'm the Director of Business Development for Core Power based in London. We feel that the shipping industry has sort of become the backbone of global trade, really largely because of the diesel engine. It's proved to be very robust, it's cheap to build and it's cheap to buy, but it's expensive to operate comparatively, and it burns the leftovers from the refining process that over the next few decades we must leave behind, along with the pollution that they create. And that means switching to zero carbon fuels, quite often for smaller engines. And to really make sense, it means a full replacement of some of the largest diesel engines. So for the nuclear industry to evolve into one that creates civilian technologies as manufactured products instead of constantly one-off large construction projects, it needs to find a market that can accommodate these large numbers of identical type-approved clean energy systems. So whereas nuclear is a true zero-emission technology in desperate need of expanding into new markets, maritime is a market in desperate need of a true zero-emission technology. So the combination of the two does have a certain inevitability about it, but it has to be done in the right way. Now, knowledge about the nuclear industry currently amongst commercial maritime is limited to fairly small specific pockets. And broadly speaking, there's little knowledge of the maritime sector amongst the wider nuclear industry. So Core Power was formed in 2018 to try and bridge that gap and to create an organization that can pave the way for deployment of advanced reactor technologies, both as offshore installations and on commercial ships. So more specifically, these are some of the areas that we're involved in. However, I think the most important are arguably the first one and the third one, actually, in the sense that we co-fund and co-develop advanced reactors that can be made appropriate for use at sea. And we're at the forefront of the efforts to sort of update the regulatory landscape so that that technology can be deployed when it's ready. I mean, the other mission statements are, of course, important too, and I'd probably highlight the last one, which is, I guess, our execution risk, if you like, is of eventually developing a mass manufacturing capability for some of these nuclear technologies is a big piece of our work in front of us. But shipping as an industry, as a global industry, has two main challenges in front of it. It has to produce less waste and emissions in the part to sort of stop the warming of the planet and to slow that change in our climate caused by the release of waste and exhaust gases into the environment. But it also must remain economically competitive. Shipping is one of the world's most fiercely competitive markets. It's not a team sport. It serves more than 80% of global trade. So it's really essential that it can continue to do that in an economic manner. And that means sort of maintaining the conditions for a competitive market that both innovates and creates. And it's really the energy use and the energy efficiency that sit at the very center of that. So the global push for a just energy transition and an environmentally sustainable ocean transportation sector will, at the end of the day, come down to the matters of energy density and energy efficiency. Simply put, the more fuel we use, the more waste we produce, and conversely, the less fuel we use, the less waste we produce. That's why energy content really matters. So the current low sulfur intermediate fuel oil, IFO 380, contains on average 41 megajoules per kilogram. It equates to just over 11 megawatt hours per ton of fuel consumed. And the industry's focus on moving to synthetic fuels made from green hydrogen, really, and they contain less than half the energy of current bunker fuels. So green methanol contains just 20 megajoules per kilogram, and green ammonia slightly less than that. So the blue box is where we are now at the moment, and moving from there to the left of down this energy density spectrum would result in an increase in our fuel consumption of more than 100% in some cases, and as stated, a corresponding increase in the waste we produce and the emissions footprint. And this is really where new nuclear can come in. Nuclear fuel from uranium, which has been safely and efficiently used in power generation and the world's nuclear navies since the 1950s, contains 80 million megajoules per kilo, the equivalent of 22 million megawatt hours per ton of fuel. And for an easy comparison, that's about 4 million times more energy per ton of fuel than these proposed alternatives of ammonia and methanol. So the physics tells us that the quantity of fuel and the fuel efficiency then guide the amount of waste that we produce. So unused carbon in the exhaust, vessel exhausts, and from the burning of the bunker fuel mixes with oxygen in the air and creates approximately 3.2 tons of CO2 per ton of bunkers consumed. So that's how the shipping industry contributes 2.5% of the 50 billion tons of global CO2 emissions every year. Now, using LNG and green methanol would somewhat improve on this. In green ammonia, it's the pilot fuel that's required to start that would actually be the only source of CO2. But with nuclear fuel, since we use so infinitely little of it, we only produce very, very negligible quantities of waste. And that waste, that final product, whilst it is toxic and harmful if ingested, it's obviously never released out into the environment like we do currently with exhaust gases from ships. So if it's not delivered to the environment and it's not ingested, it's logically not harmful. So to sort of summarize those last two slides then, shipping is currently in the grey box on the left-hand side. We know that substantial penalties are coming down the track in the form of carbon taxation. We're subjected to large swings in the price of fossil fuels, and we have to travel at economic speeds to save fuel rather than at the optimal design service speeds. The middle section in blue is one option for shipping, where it provides some compliance with the environmental rules and regulations. But in order to do that, the ships will have to reduce their cargo volumes to make way for the larger fuel tanks, which will be filled with this less energy dense, low carbon fuels. And they'll have to sail even slower, and they'll still have to connect to the shore power when they're at the berth. The right-hand column in green is the disruptive option. This is what's possible with new nuclear on board. The vessels can carry more cargo. So the large fuel tanks that were there can now be converted to cargo space. They can sail faster, even exceeding in some cases the old design service speeds. And they can actually provide power to the ports that they call at when they're at the berth. And they can do all this with true zero emissions. It sounds great, but nuclear is not necessarily easy. Substantial challenges lie ahead. That's in terms of technology, integration, regulation and financing, and of course public liability. But work by ourselves at Core Power and sort of some third-party expert groups has done some research into nuclear technologies that could function for the shipping industry, and really concluded that there are three key criteria that must be met for this generation of reactor technology to be really accepted in the marine markets. The first criteria is to have exceptional fuel efficiency of new nuclear, which could in fact provide a fuel cycle that lasts an entire lifetime of a ship. This would then remove the need to refuel reactors and remove the need for handling of fresh nuclear fuel and spent nuclear fuel in ports around the world. The second criteria is the new nucleus for marine must become affordable, mass-produced, mass-assembled products. And to achieve this, we'd need to see quality manufacturing of modular designs and modular construction of these integrated reactor and power conversion systems. And finally, for nuclear electric powered ships to call into ports and to transit canals and waterways, we'd need to see the emergency planning zone, or the EPZ, which is required around all reactors, whether on land or at sea, to shrink down to be within the boundary of the ship, something Truls picked up on there in his piece. Now, to achieve that, the reactors must be small and unpressurized. And with ambient or no pressure in the reactors, no radioactivity could then physically be dispersed outside into the environment in case of a leak or in the very unlikely case of a malfunction. So this EPZ, this emergency planning zone, really matters, and it's probably the primary reason why nuclear as we know it today has not been widely adopted by the shipping industry. It's essentially the difference between unlimited liability of maintaining a large EPZ versus the limited liability of maintaining a small EPZ contained within the boundaries of the ship. And the examples that you see here are sort of illustrative of this point, really. With a large EPZ, the red dashed line, the operator of the vessel would be responsible for evacuation and cleanup of the area in a port, or in some cases, a whole port city in case of an accident or an incident. But with a small contained EPZ, the green dashed circle, that liability wouldn't extend beyond the railings of the ship, and it could be covered then by marine insurance. And that's a very big difference. In the case of waterways, as you see on the right-hand side, where the EPZ, the planning zone, is moving along with the vessel, a large EPZ is an almost inconceivable liability burden for even the biggest vessel operators in the world. But again, a small EPZ not extending beyond the hull boundary changes sort of all of that in one go. Now, marine accidents do happen. We can't assume that a nuclear vessel will be somehow immune. However, the reason that we're working with the advanced reactor types that we've chosen is precisely because they perform so well in adverse scenarios. They have passive safety systems fitted that will shut down automatically in the event of an accident, even if no one is left on board to do so sort of actively. And these fail-safes can place the reactor into a hold-down mode from which the power can be restored relatively easily if the situation is quickly resolved, or they could actually shut the reactor completely. If a vessel containing a molten salt reactor were to sink, having shut down, the fuel salts would eventually cool and they would solidify inside the reactor itself to this rock-like substance. And the reactor would be completely sealed inside its compartment. There would be no chance of the contents leaking out into the environment. But with fossil fuels, however, the consequences are actually much more severe. And with a new generation of low-carbon synthetic fuels that are derived from hydrogen, there actually comes with it a different set of risk profiles. The toxicity of ammonia, for example, is already proving to be something of a challenge for parts of the shipping industry to actually prepare for. Nuclear security.
2 minutes, Toby. Yeah.
Sure. Yeah, I'll rattle through this. Nuclear security is also a very relevant point. Nuclear ships may be perceived as targets, but there'd be an extremely sort of robust set of deterrents and safeguards in place to mitigate that. We're talking several levels of defense in depth conceived from the design stage onwards. As I mentioned, that reactor is completely sealed inside a inaccessible shock-proof compartment. It has an impenetrable ring of steel and concrete around it. It'd be quite impossible for a bad actor to gain access. And I think even if he could, removing a parcel of molten salt fuel to use for whatever purpose would be several orders of magnitude more challenging than envisaged. But I'm going to move on from there in the interest of time. This is an important slide, and getting to the end now, which covers much of why we think this can be such a disruptive technology for shipping and the offshore sectors. Conventional nuclear on the left is excellent at what it does, but it's not suitable for commercial shipping as it stands. The solid fuel assemblies that require frequent refueling could make port calls, a real challenge. We also have the challenges with the high pressure environment that we spoke of earlier, the EPZ, and you can see that nuclear concrete pressure dome there on the left. Also, crucially, having the nuclear fuel and the coolant, water in this case, as separate items means that a loss of coolant accident is potentially possible, even if not likely. But with new nuclear on the right-hand side, all these challenges are solved. You have a liquid fuel salt that is a combination of both the fuel and the coolant, so it can't suffer a runaway thermal event. There's no pressure in the system to expel any materials to the outside. And this liquid fuel then allows for inline refueling, meaning that the vessel wouldn't need to be taken out of service for that task. And the incredible fuel efficiency of these liquid-fueled reactors operating in the fast spectrum means at the end of the vessel's life, there's correspondingly a tiny amount of final waste to process. We've calculated that after 30 years of operating one of the world's largest container ships at 30 knots, you would have a final piece of waste of around 600 kilos, about the size of a refrigerator. And that would never be delivered into the environment, and it would be handled in a process that the nuclear industry already knows very well how to do. And I've got...
we would like to have a little bit of time for questions, Toby. Is it possible to wrap it up there?
This is my last slide. Just a quick thing on the development timeline. It's shown here. Importantly, this is one of only a few reactors actually being built. We're approaching the full testing of the prototype with fissile materials in 25. The integrated effects tests are underway already and going well. And we will then look to have a full-size demonstration machine between 25 and 28. And the project order book could open from around 2030.
Yeah, that's great.
An abridged version there of that one. But thanks very much.
Thank you very much, Toby. That was very interesting. Could we open up the floor to some questions? Again, raise your hand if you have a question. Okay, well, I have a question. Go ahead.
How you deal with the corrosion in the metal system? Coating or something like that?
Yeah, corrosion was a problem for some of the very early molten salt reactor experiments that were run in the 50s and 60s. But I think even in that case, a lot of the challenges were resolved over time, although funding was sort of slowly pulled in favor, and the PWR took over as the sort of predominant nuclear technology that then evolved into providing grid scale power mostly around the world. With the advancement of modern materials and supercomputing, a lot of those corrosion problems have now been solved, and there's a very high confidence amongst our partners in TerraPower in Seattle that those problems have been solved. A lot of it relates to the purity of the chloride salts and enriching the salts to the right level of purity, so that the corrosion is mitigated. But they've done many hours of testing now, and I believe those challenges are not so much of an issue.
We have a question from Kirk Franklin.
Hi, just a comment on the corrosion issue. I recently read a paper by TerraPower detailing the large number of hours they've spent on that. The results were very poor, severe corrosion in all specimens that they looked at, and this is even before the introduction of actinide materials. So I just don't think you can make that statement. All the corrosion work that was done for molten salt work back in the 50s and 60s was in fluoride systems. This is a chloride system, it's totally different. So corrosion's a huge problem, and one that is not yielding to solution there. You need to go review the published work coming out of your partners.
Thanks, Kirk. Perhaps one more question.
Adrien, Cahier.
Adrien.
Hi.
Yes, it was about capacity of the future vessels to go from some country where at least like Australia, that nuclear power is totally forbidden, and what can it impact in terms of legislation you will have to cross over the sea and to go in different country, because it's not the same in everywhere.
Yeah, that's true. We see that certainly initially the initial project vessels will probably only trade between a fairly limited series of OECD countries that have both a strong nuclear regulator and a strong maritime regulator, and those vessels will probably only be flagged in those jurisdictions. So I think it's correct. We're not going to see the growth of a massive tramp market for these ships crisscrossing the globe from the word go. It will be probably the formation of sort of nuclear maritime corridors between US, UK, Japan. I would pick as the first three nations likely to be involved in these endeavors, and it may grow on from there. But I guess the fact that Australia is now in the AUKUS partnership and getting access to nuclear submarines may change things in the future. Obviously, they have a massive export of coal and other aggregates going north to Japan, so it's possible that may change. But I think you're right; they probably won't be amongst the first cohort of countries where nuclear ships will operate. That said, we're not necessarily waiting for IMO legislation to rewrite the rules for us. I think it would be quite possible to trade nuclear electric ships under UNCLOS rules, a bilateral agreement between two states. So we'll have to see how that develops.